All right. The next section is similar to what we've been doing, but a little bit different. What we were looking at was all about taking two different samples and making hypotheses about those two samples, but they were related in some way. So those are called dependent samples because they were the matched pairs design. It was, somebody did before and after, or somebody did the same trial twice, or they were somehow related. We didn't just randomly pick two things and compare. We want to also be able to compare data that isn't a matched pairs design. So these are going to be independent samples that we're going to look at. Maybe I want to make some kind of comparison about the rainfall in Monroe City versus the rainfall in New York. Can I really make a matched pairs design off that? No. Now, if I were doing rainfall here in 2019 versus rainfall in 2009, we could do some kind of matched pairs. But if I'm taking different sets, we have to have some different options. So, on this, you've got your formula sheets. If you look on your formula sheet, this is on there. So we talked about the pieces that we've done on this formula sheet in Chapter 11 were the t-value and the confidence interval for the matched pairs data, because we didn't cover the first two things. And then we are doing the same thing over on the second column, the t-value and the confidence interval for two different means, so independent samples now. So this t-value looks a little more complicated. Because you are taking the means and standard deviations from multiple samples and putting them together. So this is a big, lovely formula. We have it on the formula sheet, so you're not memorizing this. What you do need to watch on this, we are still requiring normal populations, but the degrees of freedom we have to watch. In this, you have two different samples. Since it's not matched pairs, they may have different numbers of values. I may have one sample that has 20 data points and the other has 7. When you decide your degrees of freedom, you have to base it off the smaller sample. So if I had a 20 and a 7, how many degrees of freedom would I do? 6. We base it off the 7 and subtract 1 to get 6 degrees of freedom. Yes. So you have to watch that. If the numbers don't match up, you always go with the smaller when deciding that. All of our requirements are the same. Independent, simple random sampling. We are still requiring either normally distributed or both samples being 30 or more. And it can't be more than 5% of the population. So the big thing that I will ask you to be watching for on the problems, did I either tell you it was normal or do we have 30 or more? Most of the time I'm just going to tell you it's from a normal population because we're looking at the raw data. I don't really want to give you 50 points to enter in your calculator because there's a lot of room for error there. So, process, very similar. Our hypothesis looks a lot alike, but you'll notice the null hypothesis has changed. So when we just had one sample, our null hypothesis was always that the mean equals something. Then when we did a matched pairs, it was that the mean was 0, that there was no difference between them. What we're looking at now is, are the two means the same? So our null hypothesis will be the mean of the first equals the mean of the second. And then your alternative will be the not equal to, less than, or greater than. So let's have our alpha, we'll still calculate our t, and then using our degrees of freedom, we can read from the table. We still have our classical versus our p-value approach. Like we've done all the others, the first example I will show you all of the approaches, and then we'll just kind of mostly do the calculator on these, because once again, these are involving the t distribution. The table that we have for the t distribution is not completely accurate because it doesn't have every possible probability at the top, so it's more accurate to rely on our calculator. So let's take a look at an example. A researcher wants to know whether state quarters had a weight that is more than the traditional quarters. He randomly selected 18 state quarters and 16 traditional quarters, weighed each of them, and obtained the following data. Test the claim that the state quarters have a mean weight that is more than the traditional quarters at the alpha equals 0.05 level of significance. Okay, so we always start with our null and alternative. So my null hypothesis will be what? You can call them 1 and 2 if you want to call them like state, S and T for state and traditional, if that helps you, whatever you need to do there. So the alternative, I want to know if the state have a mean weight that is more than. So I want to know, is the mean of the state more than the mean of the traditional? All right. So let's talk first about doing it by hand. By hand, we would have to calculate our t statistic. If you're going to calculate this t statistic, you need a lot of pieces of information. I need the x bar for both of them, sample standard deviations, my n's. How would I get those? Okay. So go to your graphing calculator. I want you to enter your state in L1 and your traditional in L2. We're not trying to prove that the difference is 0. We don't have any hypothesis about the difference between, so you don't need L3 to be the subtraction of the two. Now, if I'm going to do this by hand, well, semi by hand, because I've already put all my data in my calculator. If I were going to calculate my t by hand, I need a lot of information about these, so I need you to go to Stat, Calculate. I need it for each one, so 2 variable statistics. Now, you need to reset some things. Your X list, you need to set that to be L1. Your Y list should be L2. And then we should be able to calculate. Oh, hold on. It's not going to let us do it because we have different sizes. We're going to have to do them one at a time. Okay, let's do this again. Stat, calculate, 1 variable statistics. Let's just do L1 first. Okay. So for each of these, let's kind of jot down. So for the state quarters, the X bar is 5.7022. We need the standard deviation. So that's 0.04965. In, how many did we have on this one? 18. Okay, now we need the same thing for the traditional. So you're going to go to Stat, Calculate, 1 variable statistics, but change your list to L2. So I get X bar to be 5.6494, standard deviation 0.06894. My N this time is 16. Bless you. Okay. Everybody look at your formula sheet as we do this T formula so you know where it's coming from. So my test statistic, my T of 0. X sub 1 bar minus X sub 2 bar. So this was my L1, my L2. So I'm going to do the state minus the traditional. Minus, okay. Do we have the population mean given to us on these? No. We need mu of the first minus mu of the second. However, our null hypothesis is that those things are equal. If the null is true, what would happen when you subtract them? You get 0. So the difference is just going to be 0 for this.
Not be all of them? Not be all of them?
Yes. Just like on the dependent ones, we just, we talked about like the formula sheet has the d bar minus the mu, and we just dropped the mu because it was 0. Divided by our square root. Standard deviation of the first squared over the number in the first plus standard deviation of the second squared over the number in the second. All right, calculate this. It doesn't have to have. You really just need parentheses around the top and then the square root on the bottom. I get a t value of 2.53. We would have our different approaches. The classical approach, which I like to show you just for your reference, but that's not the approach I will ever ask you to do on the test. If I went to classical, what this t value means. We were testing if we were greater than that, right? When we look at this, we need to know how many degrees of freedom are we using in this problem? 15, because you have to look, this one was 18, this is 16, so 16 minus 1 is 15. What was my alpha level that I wanted you to test? Okay, so the classical approach says we have to find our t value to match the degrees of freedom in the alpha. So at 15 degrees of freedom and 0.05 for my alpha, we get the t to be, okay, in picture form. That means here's my t. Anything above that, we would reject. Anything in that shaded region. The t we calculated for our problem was 2.53. So would we reject or not?
Yeah.
Okay. P-value approach. So if I want to look at this, we need to, based on our degrees of freedom and our t statistic that we found. So if you go to 15 degrees of freedom, in that row you want to find the closest to 2.534 that you can. And what do you get for the probability? 2.602 is the closest you can get, so if you go up, the probability of that is 0.01. Remember, if p is less than alpha, we reject. Our alpha was 0.05, that's less, so we would reject. Okay. So there's the by hand for both. But we know, what's our preferred method on these problems? calculator because there's a lot of room for error on these. So let's go back to our calculator. We already have our data entered into our L1 and L2. So now we are going to go to Stat, Tests, and this time we have two different samples. We are talking about the mean, so that means t-test. So we need two sample t-tests. So that is number 4. Okay, now we have to decide a lot of stuff. Do I want to base this off data or stats? Data on this one because I've entered everything. So switch it to data. Okay, your list 1 should be L1. List 2 is L2. Both frequencies should be set at 1. What was my alternative? Greater than 0. It asks for pool, just keep that as no. It will always be no. And then go down to calculate. Alright, so in this, the t-value it gives us is 2.5367, so very slight difference between ours because of rounding error. The p-value is 0.0086, so our 0.01 was a little high. But again, since p is less than alpha, you reject your null.
But like that would round up to 0.01, so it's just like
Yeah,
Just like a
it's
full round.
it's not a huge difference, but it is slight. So any of these methods, we get the same answer. Let's write a conclusion sentence. So there is sufficient evidence to conclude the state quarters have a higher mean weight.
Okay, but like I thought they were like all just like put in a machine and like melted down and like pressed. Like so why would they be different?
Because they had more designs on them, so they're raised.
Interval then? We've done confidence intervals for all of these things, so it's pretty much the same principle here. Formula is a little more complex because you're pulling data from 2 different sets and combining them together. But we can either do this by hand or on the calculator. This one's not too bad to do by hand though, so let's take a look at these.
Speak for yourself on that. Honestly.
You guys have such a bad attitude. It's fun.
What?
Okay. What is wrong with you people? Okay, we want to construct a 95% confidence interval for the difference between the weights in the quarters. So let's do it by hand, and then we can talk about on the calculator. That way, if I ask you to do either way on the test, you would be prepared. So if you look on your formula sheet, it has this nice formula for you. Of course, it's on the slide before on your notes handout, so it's all there. We need a lot of the information, but we've already calculated most of this. The one thing that I need to gather, though, is my t alpha over 2. Since I'm talking about 95, my alpha is 0.05. So this is t of 0.025. We had how many degrees of freedom? 15. So, going from your table, your t distribution, 15 degrees of freedom, 0.025 gives us. And now between this and the last problem, we have everything we need to plug into our formula. So it is the x bar of the first minus the second, so 5.7022 minus 5.6494, plus and minus the 2.131 square root, standard deviation of the first squared over n of the first, so this is really kind of like our t statistic. 0.049. What was it?
6.0. Negative 6.0.
6.5 is what I have. And that one was 18 plus this one was 0.06894
Wait, really? Okay, yeah, these are
over that one was. So type this in your calculator. And if you're not going to participate right now, then I will make you do them all by hand on your homework assignment and not let you use the calculator.
Like, I'm participating, but it might be tomorrow by the time we get all this type in the rest.
Well, I forgot how to even find the comprehensive ones. Like, I've been doing them.
They're not that bad to do by hand. You already have all the
It's
information.
just like there's so many things I have to do on the calculator. If I can just plug this in and be okay, I'm just gonna do it.
Yeah. So that's kind of annoying. I prefer to do these by hand. So I got 0.0084 and 0.0972. So I am 95% confident that the difference in their weights falls in that interval. So would that lead you to believe that their weights are different? If their weights were the same, what would...
0 doesn't fall in between them, so yeah, they're different.
Yes. If their weights were the same, there would be a 0 in the middle of that. There's not, so that would also lead me to reject the null, and the weights are different. On the calculator, if you want to do this confidence, didn't get crossed out, confidence interval on the calculator, you need to go to Stat, Tests. Now let's see if you guys can figure out which one you need. Are we talking about a Z or T? T. How many samples do we have? 1 or 2?
2.
And we want an interval. So you have to keep going down. And you need
The
Wait, no, you're 2 sample T interval.
the 2 sample T interval.
What's our C? 0.95.
So that is 0, I believe, on your list. So if you go into that, we're basing it off data. Make sure your list 1 is L1, list 2 is L2. Frequency is 1. Confidence level, we're at 0.95. Do not do pooled. So pooled is no, and then calculate. And it gives me slightly different because of rounding error. But they're pretty close. Do you have a question?
What was the C value? But I just keep it over that. I had it in at 0.9.
Oh. You did your sense.
Did you ever go back and fix your data?
I don't know.
You were talking about the I don't know why I had 0.9. I already had 0.9.
Probably from the last time it was done. Okay. Questions here?
Yeah, it works the whole day.
Yeah. Do them all. It's good practice. Okay. This is the